Good afternoon, everyone. Welcome back to our VKC talk. My name is Gary Fong. I'm a PhD student at the University of British Columbia studying inclusions in diamond, and I'm hosting this meeting on behalf of the Diamond Exploration Laboratory at UBC. VKC is a series of seminars focusing on diamonds and kimberlites. Our goal is to bring academics and industry professionals together. I would like to acknowledge SRK Consulting for being a long-standing sponsor. There are a few Zoom housekeeping notes for today. For the audience, please keep your microphones and cameras off during the presentation to ensure good quality of streaming. Today's section will be around an hour long. Please keep your questions until the end of the presentation, at which point I will facilitate a Q&A period. Our speaker today is Dr. Zachary Sudholz. Zach is a postdoctoral researcher at Buoyant Laboratories, University of Cambridge, and a By Fellow at Murray Edwards College, Cambridge. His current research integrates petrological and geophysical approaches to investigate crustal and mantle processes, including the growth and evolution of cratonic roots, granite emplacement, and melt transport within the lower crust. Prior to joining Cambridge, Zach held a postdoctoral fellowship at the Research School of Earth Sciences, Australian National University, where he studied mantle petrology and lithospheric structure in the Kimberley and Gawler cratons, and the newly discovered Webb alkaline province of Central Australia. He was awarded his PhD in experimental petrology from the Australian National University in 2022 under the supervision of Greg Yeley and Linton Jacques. His doctoral research focused on the experimental recalibration of mantle geothermal barometers and the application to mantle xenolith and xenocryst suites from Australia. Zach's work takes an interdisciplinary approach to understand the crust and lithospheric mantle, combining experimental and microanalytical techniques with thermodynamic modeling and geophysical methods. Zach, the stage is yours.
Wonderful. Hopefully everyone can see the screen. Oops. Well, wonderful. Firstly, thank you for the opportunity to present, and it's great to see many familiar names here. So yes, as Gary mentioned, I'm a research fellow at Bullard Labs. The work I'm going to present today is mostly ideas and work that sort of stemmed from the last 6 to 12 months, predominantly focusing on trying or understanding how cratons have changed through time, with a particular focus on trying to understand how lithospheric thickness and the thermal structure has varied from present to the Proterozoic and Archean. So I think the general properties and features of the Cratonic lithospheric mantle will be familiar to most people here, but just to make sure everyone's on the same page, I'll go through some of the key features and properties of the Cratonic lithospheric mantle. So generally, cratons are regions of thick, cold, and tectonically stable lithosphere. They often make up the cores or the nuclei of most continents. And depending on who you ask, there's anywhere between about 35 to 45 cratons on Earth. And the general locations of these cratons are shown by these pink polygons here. And I think many of these regions are quite familiar to people in this room or in this meeting. So the Cratonic lithospheric mantle is quite unique in the rocks and compositions that make up the mantle. So generally speaking, the Cratonic lithospheric mantle is made up of depleted lersites, most notably harzburgites and dunnites, which are characteristic in their relatively high modal portions of olivine and lower modal portions of clinopyroxene relative to non-cratonic regions. These rocks are also associated with a relatively unique chemical composition, most notably their high magnesium concentrations and low iron concentrations relative to non-cratonic mantle rocks. So these higher magnesium and lower iron concentrations of mantle rocks from cratons is often expressed in a magnesium number, and when we compare those values with magnesium numbers from non-cratonic regions, we can see that typically these values range from about 91 to 94, whereas those from non-cratonic regions are typically much lower. So these magnesium numbers that make up the mantle rocks from cratons, it's widely accepted that they are produced from very high degrees of partial melting, typically on the order of about 20 to 40%. And these kind of values for the amount of partial melting have been reproduced from various experiments, but also from various thermodynamic models as well. It's also well constrained that the partial melting, in order to produce these anomalous chemical compositions and lithologies of mantle rocks, took place sometime between 2 billion years and 3 billion years for most cratons. And this is constrained from methods like re-emulsion and geochronology. So we know relatively well that during this period, most cratons experience quite a significant partial melting extraction event that essentially produced this depleted residue that makes up the vast majority of cratons that we are familiar with. So we owe a reasonable or quite a large proportion of our understanding of the cratonic lithospheric mantle to present-day observations from geophysical methods. So for example, methods like seismic tomography and receiver functions provide quite a strong understanding or robust understanding as to the thickness of cratons in their present-day form. So the vast majority of cratons have present-day thicknesses on the order of about 150 to 250 kilometers. Obviously with some exceptions. And sort of the typical values that we see for cratonic lithospheric thicknesses are shown here for some examples in Australia. So for example, places like the Yilgarn Craton and Kimberley Craton have values of around about 200 kilometers. And if we were to expand these maps on a global scale, we'd see that with the exception of a few cratons, the vast majority of locations will have present-day thicknesses within this range. So another important and diagnostic feature of cratons in their present-day form is their relatively unique surface heat flow. So most cratons have a surface heat flow value between about 35 to 45 milliwatts per square meter. And this is much lower than most active, younger geological terrains on Earth. And these lower surface heat flow values of cratons are partly due to their much older ages. So it's allowed radioactive elements to decay through time, limiting the amount of heat production, but also the fact that most of these cratonic regions have experienced significant depletion within the crust and mantle, which has essentially stripped out a lot of the heat producing materials. Another important feature or diagnostic feature of cratons in their present day form is their unique gravitational structure. So the vast majority of cratons on Earth, when we look at their free air gravity anomaly, have negative values or values fairly close to zero. And this largely relates to the fact that cratons are dominantly neutrally buoyant. And this has got to do with compositional and temperature controls. And I'll discuss more of that in detail later. But the vast majority of cratons have relatively low or negative gravity free air anomalies. And an area that's been quite popular over the past 10 years is sort of this chemical tomography approach, where various different geophysical methods are incorporated to try and understand the present day composition and structure of cratons. And these certain methods have confirmed that the vast majority of cratons in their present day form are also highly depleted, which to most petrologists is not a huge surprise, but nonetheless, these are important observations and pertinent data that tell us about what cratons are like in their present day form. Now, a major challenge and major problem in our understanding of cratons is that how the temperature, thickness, and composition of cratons was back through geological time is relatively poorly constrained. So in present day, we've got various geophysical methods that provide us with good observations and good constraints of these different parameters, so composition, thermal structure, heat production, and so on. But as we go back through time, really our understanding of the cratonic lithospheric mantle is significantly limited. And often it's limited to small point analyses through time for events such as kimberlites and mantle xenolith sampling. And so one area that I'm particularly interested in, I think an area that's quite important that a number of people are working on is trying to understand how the Cratonic lithospheric was like back through time, and particularly whether cratons in their past have similar structures, compositions, and temperatures to the way we see them present day using different geophysical techniques. Now, understanding whether the temperature, the composition, and thickness of the Cratonic lithospheric mantle has varied through time and whether it was significantly different in the past is important for a number of reasons, both academically but also for mineral exploration. So, for example, there's a large number of ore deposits that are controlled or appear to be controlled by lithospheric thickness. Uh, we know quite well that the volumes and compositions of many magmas are directly correlated with lithospheric thickness. Uh, the thickness and composition and thermal structure of the mantle also controls different tectonic regimes and how mantle is recycled or the crust is recycled. It also obviously controls things like volatile storage and degassing. So areas where it's thick and cold are often quite favorable for storing volatiles over long periods of time, which obviously plays an important role in climate cycles and carbon storage. And perhaps most importantly and most relevant to the audience here is that uh, lithospheric thickness and its thermal structure directly controls or contributes towards diamond preservation, also kimberlite formation. So if the Cratonic lithospheric mantle has changed thickness through time and whether it's been secular through time is quite important because it affects where people may or may not find diamonds as part of exploration. So arguably the best and probably the only way to study in detail the changes in lithospheric structure and composition through time is through the use of direct sampling of that region, either from pieces of mantle that have been incorporated in melts that have transported from beneath the Cratonic lithospheric mantle to the surface, or more rarely from tectonic exhumation, so ophiolites and related terrains that provide snapshots of the composition of the mantle as a result of uplift and exhumation. So in this particular talk, I'm mostly focusing on mantle xenoliths that have been brought to the surface by kimberlite and related volcanic eruptions. So this is all area that I think is familiar to most people here, but the vast majority of these magmas form within the convecting mantle or lower lithosphere and travel to the surface within a matter of hours or days. And this rapid sampling is quite important because as these kimberlites and related rocks pick up mantle xenoliths and xenocryst, this rapid transportation prevents those xenoliths from thermally re-equilibrating and compositionally re-equilibrating. And that's important for this work and for studying how the cratons evolve through time because we can essentially collect these mantle xenoliths and xenocryst from different age kimberlites and different locations to get snapshots of what the composition and thermal structure of the mantle was at the time of the eruption. Now, kimberlite and related eruptions have occurred all throughout Earth in terms of where we have cratons. At least current databases of the locations of kimberlites and related rocks pretty much cover the vast majority of cratons on Earth. And this is all largely as a result of diamond exploration that's been done over the past 50 or so years. Additionally, in addition to the geographical coverage of kimberlites, they also cover quite a large range in ages as well. So kimberlites span from near present day all the way up to the Proterozoic and some slightly older than that. Now, obviously, the vast majority of eruptions are quite early or quite recent, and this is perhaps a cause of due to preservation, but also potentially changes in the dynamics and mechanisms by which these melts are formed. Regardless of this trend, if we can have access, or if we can access mantle xenoliths from some of these older kimberlite eruptions, they provide a tremendous resource for trying to understand things like the thermal evolution and change in thickness and composition of the Cratonic lithospheric mantle, which we can compare with present day observations from our different geophysical data sets. So in this particular work, I'm using a global data set of mantle-derived xenoliths and xenocryst that has been compiled over the past few years. largely as a result of huge amounts of literature that's been done on this material. So, although some of the material is my own that I've collected from Australia, from part of the research I've done there, the vast majority of data is from industry and from scientific publications over the past 40 or so years. I'll discuss a little bit later on about this data set and where you can access it, but this data set sort of covers samples from the vast majority of cratons on Earth and eruption ages from 20 million years all the way up to 2.1 billion years. Obviously, if the vast majority of samples sort of covering that 0 to 500 or 600 million year range. So the samples that I'm using for this study are mostly xenocrysts. So these are essentially single grains of pieces of peridotite that have been brought up to the surface by these different kimberlite and related volcanic eruptions. So particularly I'm focused on clinoproxene and garnet xenocrysts. These materials provide important insights into the composition, but we can also use them for geothermal. So the clinoproxenes in the data set, the vast majority of them are from a peridotite source rock, a garnet peridotite source rock for that matter. We do include, or I do include some that come from pyroxenite sources, and the reason for that will be discussed in a little more detail later. But the vast majority of these are all coming from garnet peridotites based on sort of the compositional filters that we apply. The garnet xenocryst in this data set, I'm not going to touch on too much about garnets, but there is ongoing work using these. But these cover a whole range of different peridotite compositions, as well as some more exotic samples like eclogites and pyroxenites. But I'm not going to touch on too much detail about this. This is largely ongoing work. So for the clinopyroxene data, we can use single grain geothermal to try and constrain the pressures and temperatures at which these samples equilibrated at. So the conditions that they were in the mantle before they got brought to the surface by these rapidly ascending kimberlite magmas. And to do this, we use the single grain geothermobarometer of Sudholz et al. 2021. And this is based on essentially the chromium concentration in single grains of clinopyroxene. We also use the geothermometer of Nimbus and Taylor 2000, and this is based on the answer type proportion in clinopyroxenes. And so by iteratively solving the temperature and pressure, we can get a robust estimate of where these samples came from within the mantle. Importantly, because we're applying these thermobarometers to single grains, we also must use quite careful protocols on filtering. In this particular work, we use the filters of Zberner et al. 2016. And these are a robust set of methods and protocols that essentially remove out clinopyroxene compositions and PT estimates that either don't fall within the calibration range or are inconsistent with a peridotite source rock in the mantle. We also use some whole xenoliths in this dataset, and the purpose of those will become more apparent later on. But for these, we use a number of different geothermobarometer calibrations, depending on whether key minerals like orthopyroxene and clinopyroxene are present. And I'm happy to discuss that in more detail later. But when we apply these different thermobarometers to our entire dataset, we can see that typically the temperatures and pressures range from a little bit above 2 gigapascals and 600 degrees, all the way up to slightly over 8 gigapascals and 1450 degrees. And the range in temperature and pressure estimates for the whole xenoliths and the xenocrysts are relatively consistent with one another. We also apply the thermobarometers to single grain clinopyroxene or diamond inclusion xenocrysts as well. So these are essentially clinopyroxene xenocrysts within diamonds. And a lot of this data comes from Thomas Starkel's data set. And again, we can see that across these different locations, the temperatures and pressures of these diamond inclusions broadly cover the kind of PT range that we observe for that whole xenocryst and xenolith data set. This on its own is quite interesting. There's been a few studies over the past couple of years that have suggested that some of these diamond inclusions may be recording fossil ancient geotherms from the Archean. At least when we compare the pressures and temperatures with sort of global data sets, they don't really record anything particularly anomalous at least sort of on this global scale. So one of the useful things that we can do with these pressure and temperature estimates from these different age kimberlites and different locations is that we can essentially compute geothermal gradients or paleogeothermal gradients that tell us what the potential lithospheric thickness was at the time of eruption. And so the way that we do this is that we have enough pressures and temperatures, we can essentially fit a geotherm through that. And where that geotherm intersects the adiabat at a given potential temperature gives us some idea as to what the thermal lithosphere sensitive boundary is. This is quite a useful parameter because we can compare thermal LAB estimates with present day values from different seismic methods such as tomography and receiver functions. In this study, we're particularly focusing on the thermal LAB. There can often be some inconsistencies in terms of whether people are comparing the mechanical LAB or the thermal LAB. Everything I'm talking about in this study is strictly the thermal LAB. In order to compute the paleogeotherms, we use a revised paleogeotherm modeling method that was described or discussed in Sudholz and Copley 2025. And for those that have used FitPlot previously, this is essentially the same as FitPlot. It's all the same underlying dynamics, except it just runs significantly faster and deals with much, much larger data sets. And the benefit of this will be discussed in the next couple of slides. So when we compute paleogeotherm models, the traditional approach of using FitPlot would involve the user providing the pressure and temperature estimates of the xenoliths. And so an example is shown here where we've got those dark dots which represent individual pressure and temperature estimates. And in conventional methods for doing paleogeotherm modeling, you would insert or you would input your estimated values for crustal thickness, heat production, and potential temperature. Because all of these different parameters and many others influence the shape and the properties of the geotherm. Now, obviously, a huge issue with this is that if we have kimberlite eruptions or mantle xenolith suits that erupted many millions of years ago, or in some cases billions of years ago, we don't particularly know very well what the crustal thickness may have been, what the heat production in the mantle was, or even what the potential temperature may have been. So often if we're using those original methods like FitPlot where we have to input individual parameters, that can lead to quite large uncertainties and errors in our geotherm model. So in our revised method, the way we go about making these geotherms is that rather than fit a single geotherm, we individually vary all the different input parameters that are required for the model. So things like crustal thickness, the heat production in the crust of the mantle, the MOHO temperature. We vary all those different input parameters within geologically realistic ranges, and provided that resulting geotherm can fit the pressure and temperature estimates of the xenoliths within some given tolerance, we consider that geotherm successful. And so this method, we will typically compute up to 10,000 individual geotherms and filter them out, provided if they can fit the xenoliths within some given tolerance. So typically that tolerance is within about 75 degrees or so. And so this is really useful because it allows us to get a better feel of the errors and uncertainties on our geotherm methods and gives us a sort of a range of LAB estimates. And so you can see on this example here where we've got a paleogeotherm made for pressure and temperature estimates from Argyll in northwestern Australia. Each of those, this grey region is made up of many small individual paleogeotherms that have been fit to the model. And each of these models will fit to the data within that given tolerance range. So once these models are completed, typically they only run for 2 or 3 minutes, we can extract out the values of the input parameters. So we've got a few examples here of things like crustal thickness and the heat production and heat flow. And then we've got sort of the histograms showing as to what the values of the models were. These are not particularly important in this talk. The main thing that we're interested in is extracting out the lithospheric thickness, which, as I said before, is the value at which the paleogeotherms intersect the adiabat at some given potential temperature. So a couple of examples of those are here, where we've basically got histograms of what the estimated paleo LAB depth and temperature are based on this modeling approach. So with this paleogeotherm modeling method considered, we can go ahead and apply it to global data sets of mantle xenoliths and xenocryst, where we've got a sufficient number of PT estimates that we can make robust paleogeotherm models. So here is the list of locations that I'm using in this study. It's sort of growing as a result of sort of more publications are coming out, but this is sort of the most recent iteration of the data set that we're applying this method to. And so we can see we've got samples pretty much from most of the major cratons on Earth, and these ages span from about 20 to 2.1 billion years. So this is this plot here shows the LAB depth on the y-axis, computed from the models, and the emplacement age of the kimberlite on the x-axis. I'll go into a little more detail about individual locations and individual trends in the next few slides, but generally what we can see across this data set and across the different locations is that the vast majority of these xenolith suits and xenocryst suits are recording lithospheric thickness or cratonic lithospheric thicknesses between about 200 to 250 million years kilometers. And this is consistent from the very recent data sets all the way up to some of these very older examples such as Melita and Argyll. Obviously, there's some scatter here, which is not a huge surprise. We can see a number of quite shallow examples that sort of trend below 200 kilometers, and many of these examples are for craton margin settings, which we would expect to have fairly low or thinner lithospheric boundary estimates. So I'm going to discuss some of the individual trends now. So for example, in Africa, we've got a number of reasonable or robust constraints for the cup vale craton. So for example, Cullinan and Premier. We're typically getting lithospheric thickness values for here about 225 kilometers. Because we run this model so many times, the error bars are usually quite small, but I'll discuss sort of more robustly of this shortly. But when we compare some of those estimates of in the Mesoproterozoic to more recent values, there's a little bit of variation, but not a significant amount. Again, with places like in North America, we have some constraints through time for regions like the Superior Craton, where we've got a couple of estimates through time. And again, we can see a relatively consistent lithospheric thickness through time with a little bit of variation. There's obviously some clustering here, but again, the vast majority of these estimates are plotting between about 200 and 250 kilometers. And there doesn't appear to be any major secular variation in these lithospheric thickness estimates. The pink triangles here are for estimates, lithospheric thickness estimates around the Wyoming Craton region. And there's possibly some variation in lithospheric thickness here through time. We can see that some of those estimates during the Ordovician or Devonian are slightly higher than what we're getting for more recent eruptions such as Homestead. And there's been a number of studies that have suggested that the Wyoming Craton is one of several locations that may have experienced thinning or erosion through time. Now, obviously, the estimates we've got here have got some large error bars, particularly for these recent examples. So we are somewhat cautious in trying to draw conclusions from that. But there is a possibility there is some variation beneath this particular region. Another location we have quite good data for is Australia. So one unique location is the Kimberley Craton in northwestern Australia. So here we have a number of key lamproite and kimberlite eruptions that occur within a relatively small spatial scale, but bracket a number of key events through time. So for example, Argyll, we have lithospheric thicknesses around about 250. Ashmore, which is slightly further north of Argyll, which erupted in the Neoproterozoic at about 800 million years, is again at 250. And then recent eruptions within the Allendale field are again 250 kilometers with some error. And finally, there's a huge number of different locations for Eurasia. Really, we see a fairly consistent values in lithospheric thickness, with one exception being the North China Craton. We have some estimates of lithospheric thickness during the Ordovician based on a limited set of pressure and temperature estimates. and also more recent values from basalt xenoliths from the North China Craton as well. And we can see a really strong change in lithospheric thickness here. For those that are familiar with the North China Craton, this wouldn't be a huge surprise. We know that this region has experienced quite significant lithospheric thinning or erosion, at least since those initial samples were in place during the Ordovician. So one of the sort of interesting things for this data set is that a number of these lithospheric thickness estimates bracket key tectonic and magmatic events through time. So for example, in northwestern Australia, where we have a number of famous kimberlite and lamproite eruptions like Argyll and Allendale, these bracket the Kalkarinji large-igneous province, which erupted at about 550 million years. At least when we compare the lithospheric thickness estimates on this timescale and this sort of geographic scale, we don't see any significant response in lithospheric thickness across this large-igneous province event, which is, I think, quite an interesting or important observation. Again, for places like South Africa, where we have a large number of events that pre and post date major thermal and tectonic events, we can see that there's not a significant variation. So, for example, we have eruptions before and after major large-igneous province events like the Karoo-Farrar and the Pirana-Ekdendeka large-igneous provinces. So we have estimates for Cullinan and Venetia, which again range between about 250. Within the same kind of cratonic region, after the large-igneous provinces, we can see that those values are within that kind of 200 and 250 kilometer range. I will note that some of these lower values that are occurring, lithospheric thickness estimates that are occurring during the past 75 or 80 million years, several of these are for off-craton regions. So we would expect that some of those are slightly lower. But perhaps the key takeaway from this plot is that when we look at lithospheric thickness over the length scales or the time scales of what we have here for kimberlite eruptions of almost 1.5 or 1.2 billion years, we don't see any significant variation, and particularly after these large provinces are coming through, we don't see a drastic change in lithospheric thickness. Again, we can see a similar thing for some samples from the Siberian Craton. We have a major large province that came through at 250 million years during the end of the Permian, the Siberian Traps. Again, when we look at some of the Devonian mantle xenoliths and lithospheric thickness estimates and compare those with some of the lithospheric thickness from the northern fields, we see a bit of variation, but again, the vast majority of these estimates are clustering around that 200, 250 million range. And we don't see a large decrease or secular thinning of lithosphere after these large province events. And we've seen this beneath the Siberian Traps, but also from a number of other locations, which I think is an important observation. I think it's an observation that is debated, but at least when we look at these large data sets on large timescales, we aren't seeing a significant variation in thickness across these events. So one of the important things, or one of the interesting things we can do with this data set, these lithospheric thicknesses, is to compare them with present day observations from seismic tomography. So there are a number of different geophysical methods that are available to constrain lithospheric thickness, the most notable being SP receiver functions or seismic tomography that's inverted for lithospheric thickness. In this particular study, I'm comparing my LAB estimates with the LAB seismic tomography model of Priestley et al. 2024. Again, there are a number of different models available with some variation in them. So I will sort of caution that depending on which model you use, you can often get some variation in the exact values, but as I'll show, the trends through time are relatively consistent, albeit small variations in individual locations. So for comparing our lithospheric thickness estimates from our xenolith paleo geotherms with the seismic tomography data, the way we go about doing this is to compute temperature depth profiles from these tomography models using the 4 nearest grid measurement locations that surround each kimberlite location. So in these global models, they're made up of individual grid measurements across the entire scale of the Earth. And so we take the 4 nearest grid measurement locations for each kimberlite location, and we weight them by distance. So we take the 4 surrounding each location, weight them, and compute a temperature depth profile. And where that temperature depth profile intersects the adiabat at a given potential temperature, we refer to that as the thermal LAB for the present day. Now, the exact methods by which these seismic tomography models are converted into temperature and depth, I'm happy to answer that during the question time, but for those that are interested in the exact methods, it's best to check out the work from Keith Priestley and Mackenzie et al. But essentially, these seismic tomography models are inverted to get temperature, which then gives us depth as well. And this is calibrated using a number of different observations from xenoliths themselves, but also from the temperature depth profiles of mid-ocean ridges. Now, importantly, as with everything, this method does come associated with some errors and uncertainty. The global model that we're using is based on a 2 by 2 degree grid. So that places limitations on trying to resolve very small scale variations in lithospheric thickness. So trying to resolve individual thicknesses within kimberlite provinces is probably beyond the scope of this model, but within cratonic regions, it's a relatively robust method to constrain present day lithospheric thickness to compare with our paleo geotherm LAB estimates from the past. Again, many of these geotherms, these temperature depth profiles that are computed from the tomography models have often quite complex profiles, and it can be sometimes ambiguous to determine as to where that geothermal, that temperature depth profile is intersecting the adiabat to determine where our thermal LAB is. But nonetheless, it is a reasonable and robust method for general observations and general comparisons between present day seismic LAB values and our paleo xenolith LAB estimates. So when we compare each individual location across the global dataset, we get a plot like this. So on the x-axis, we've got the emplacement age of the different xenolith locations. And on the y-axis, we've got the change in LAB depth through time, remembering that this is thermal LAB depth. And so this is calculated as the seismic LAB minus the petrological LAB. And so when we look through time, we can see that, again, there's a relative consistency in lithospheric thicknesses ranging from the present day all the way up to some of the very old Proterozoic examples that we have. Now, again, there is some variation in some clustering and some cluttering, and there is some samples with quite large uncertainties. But given that we are comparing 2 data sets that are determined using a number of different approaches, I think we've got a relatively robust and reasonable comparison to make here. So there are a number of interesting trends here. I think perhaps the ones that stand out the most is that some of these older kimberlite and xenolith suits are recording lithospheric thickness values that are essentially within 10 kilometers or 15 kilometers of the present day values that we're getting from this seismic method. So for some of these locations like Melita and Jewel, which are occurring in the Yilgarn Craton of Australia, I think it's quite remarkable that we've got an eruption that took place nearly 2 billion years ago that's got a thickness that's essentially the same as what we see in the present day. And again, we can see within the vast majority of cratons and locations, this trend is consistent through time, between about sort of 50, plus minus 50 in terms of the net change in lithospheric thickness. But I would argue that many of this sort of clustering or this scatter around plus minus 50 is simply just the noise. But we don't really see any significant secular trends in lithospheric thickness or evidence that the lithospheric thickness was significantly greater in the past. Now, obviously, there is a few exceptions here. One notable location is the North China Craton. So when we look at the paleo geotherms for this location, although they have quite large uncertainties and are based on not a huge data set, but a reasonable data set, and we compare those values with our present day estimates, we can see that there's been quite a significant change in lithospheric thickness here. As I discussed on the previous slide, for those that are familiar with this particular location, it's not a huge surprise that we're seeing this in this data set. There's a huge number of publications for the North China Craton that are demonstrating this region has experienced significant thinning and change in lithosphere since its eruption during the Ordovician. we can see some other variations. For example, some of these locations in the Wyoming Craton, there has been suggestions that this location has experienced thinning or erosion. This is completely possible. Based on the data set that we have, we don't see any significant variation. At least if it's within 50 kilometers of change in thickness, we can't resolve it very well. So there very well may be changes in lithospheric thickness that are below 50 kilometers, but we just simply can't resolve it in our data set. And that's also the same case with places like the Cutval Craton, where people have suggested that there's been thinning there. That's completely possible, but at least based on our observations, that thinning or erosion or delamination had to have been restricted to probably less than 50 kilometers, which I think is probably the main takeaway here, in that we don't think lithospheric thickness has changed significantly through time, and if it has, it's been less than 50 kilometers. Now, this obviously comes with a number of important implications, particularly that are relevant to work that's been done over the past 5 or 10 years. So, for example, one topic that's been quite interesting and quite sort of provocative in the past couple of years is the idea that cratons may have been potentially thicker in the past. And these are two papers that are very important and definitely worth reading, that have suggested, based on reasonable evidence, that cratons may have had thicker lithsphere in the past. Now, at least based on our observations here, we don't see considerable evidence for that, at least based on the observations that we are making. But I will stress that this is somewhat dependent on the potential temperature that you're using in the model. So if you invoke a model that has a very, very high potential temperature, then by definition, you will have a thick lithsphere, but we do not see that considerably in our data set. And I'm happy to discuss that in more detail during the question time. Another important observation or important implication is the idea that cratons are thinned or eroded permanently as a result of mantle plume. So I showed you a few slides ago some of the lithospheric thickness estimates that bracket major magmatic events throughout Earth's history, such as the Siberian traps, the Purana Etendeka and Karoo-Farah large-igneous provinces. When we look at the lithospheric thicknesses on either side of those major large-igneous provinces, we don't see a significant trend in lithospheric thickness through time. So we are seeing a relatively consistent value in lithospheric thickness on both sides of those large-igneous provinces where we have sufficient data. Now, this is really important because there's, again, a number of very influential and widely cited papers that are based, again, on very robust methods that suggest that mantle plumes cause significant erosion and modification of cratonic lithosphere. At least based on my observations from the paleo geotherms, but also from the compositional data, which is ongoing work, we don't see that mantle plumes are causing a significant modification of the lithospheric mantle structure or composition. Again, they might be causing slight thinning on the order of a few kilometers, but definitely not on the orders of 50 kilometers. And finally, an idea or a hypothesis that's been very interesting over the past couple of years is this idea that cratons may reheal through time. So there are a number of locations in our data set where we've got lithospheric thicknesses on either sides of mantle plumes or large provinces. And there's been studies over the past few years, again, very important papers that have suggested that cratons may thin through time, but they may also reheal through different mechanisms. Now, based on the scales of the data that we have, we can't really comment robustly on whether this is a feasible method or not, but I think it is probably a suitable approach to try and explain some of the observations that we see within the cratonic lithosphere. So many of you will be familiar that these large provinces that are occurring within cratons require the lithosphere to be moderately thinned through time. So in order to actually produce the compositions that we see in many of the large provinces, there needs to be some thinning taking place. So possibly what is happening is these cratons are temporarily thinning and rehealing, and that's a completely viable method. I will stress, however, that there are a number of mantle plumes in large provinces that don't necessarily require significant thinning of the lithosphere based on the fact that they've got some lithological anomalies within the plume head that allows for melting to occur at much higher pressures than what it would otherwise occurring within the shallow lithosphere or causing significant thinning. Um, so yes, I think the verdict is still out on that, but I think it is possibly the most suitable method to try and explain some of these observations. But again, I think further work is needed on that space. Particularly if we can have xenoliths that more closely bracket some of these large English provinces, but ongoing work there. So for the next sort of 15 minutes or so, I want to just talk a little bit about how the composition, the lithology and pressure and temperature of the Cratonic lithospheric mantle influence its stability. So over the past few slides, I've made the case that cratons are generally stable or structurally stable over very long timescales. And for the next few minutes, I just want to discuss as to why that is the case in terms of their composition and PT. So for those who are following at the start of the talk, you'll remember that I discussed that cratons, or the mantle beneath cratons, is made up of a very unique set of compositions and lithologies that are very depleted. Most notably, they have very high magnesium and low iron concentrations, at least relative to non-cratonic mantle rocks. I also discussed that in order to produce these anomalously magnesium-rich and iron-poor compositions requires quite significant amounts of partial melting or melt extraction. And we discussed that this probably took place during the Proterozoic or Archean based on the rhenium osmium data. We also know from experiments and numerical simulations that if we're extracting on the order of 20 to 40 weight percent or 20 to 40% melt fraction out of the mantle to produce these anomalous compositions and depleted residues, that is associated with quite a significant change in the density of that leftover, that residue mantle. So if we're doing a melt extraction on the order of 20 to 40%, this results probably most likely in a density change on the order of 1 to 2%. Now, this might not sound like much, but this change in density of the residue before and after melt extraction is enough to cause many of these unique properties of cratons, most notably their buoyancy and longevity through time. Now, this is not a huge surprise to probably most people. The change in the composition of the Cratonic lithospheric mantle as a result of this melt extraction plays an important role in its buoyancy structure and stability because it offsets the negative effects on density that are caused by the cooler temperatures. So essentially, we have a compositional effect and a thermal effect that almost cancel each other out. Now, this is nothing particularly new. Many of these ideas and works come from important work that was done mostly in the 70s and 80s from Tom Jordan, and this is sort of broadly the basis or the ideas of the isopycnic hypothesis, that cratons, across their most part, are neutrally buoyant because the depleted compositions that result in a lower density offset the effects of temperature that cause higher densities. And this is sort of a characteristic process or characteristic feature of many cratons around the world, or at least we think so. Now, importantly, a craton that is perfectly isopycnic, so a craton that's perfectly or nearly neutrally buoyant, will have a density structure that essentially matches the asthenosphere across an equal depth range. So this means that the density of the Cratonic lithospheric mantle is near similar to that of the surrounding mantle, which essentially allows it to float within the mantle and resist things like subduction and erosion or delamination to the asthenosphere. And I'd argue that many of the observations that we make from cratons and many of the characteristic features of cratons suggest this is dominantly correct because, at least based on our observations, we don't see cratons being significantly eroded or removed. Most cratons, that is. Now, always, there's obviously some exceptions. North China is the classic example where we see that there has to have been some change in lithospheric thickness in the past in order to explain this very anomalous shift in past versus present lithospheric thicknesses. And again, you can make the case that there's probably other locations this is occurring, but this is sort of the classic example where a craton is probably not behaving perfectly isopycnically, and there has to be something operating within the mantle to allow for such a substantial amount of lithosphere to be removed. And I'm interested to try and use the compositions and pressures and temperatures trying to explore as to what is causing that. Now, there are a number of different ways that have been proposed by which cratons can potentially be destabilized or be removed. One of the popular methods is that of metasomatic enrichment of deep cratonic heels. So, over the life cycle of cratons, they experience fluid and melt infiltration either from subduction or underlying melts. And when these fluids and melts interact with the deep depleted cratonic lithosphere, they can often cause metasomatism, which essentially generates a layer of enrichment. And in terms of the composition of mineralogy, it can cause the precipitation of a number of different phases like phlogopite, amphiboles, garnets, and clinopyroxenes as well as introduce a number of denser elements and oxides into the cratonic lithospheric mantle. So many of these metasomatic layers within the mantle have a higher net, will probably have a higher net density than the surrounding mantle. And so the idea is that the introduction of these metasomatic layers, which will have higher densities, or we think they have higher densities, they also lower the solidus temperature as well. So they often concentrate high amounts of water and CO2, which cause the peridotite solidus to be significantly reduced and allows for melting to occur at much lower temperatures. So the metasomatic enrichment of the cratonic lithospheric mantle, in summary, contributes towards the destabilization and potential destruction of the cratonic lithosphere. Firstly, by locally increasing the density, which can promote or help promote things to get removed easier by density-driven sorting, but also they lower the solidus temperature to allow things to be melted. So that's arguably, or the sort of the summary as to how these processes can potentially cause destabilization of cratons. Now, from our data set, we can try and explore some of these processes and methods in a little bit more detail. So in particular, we can look at the mineralogies and pressure and temperatures of our xenoliths and try and compute or calculate densities. So as I discussed previously, the vast majority of samples from the cratonic lithospheric mantle are things like dunnites and halite, which are essentially depleted lersites and depleted peridotites. And we think these are the vast majority of cratons are made up of these kind of rocks. As I discussed in the previous slide, though, we also know that there's some metasomatic rocks within the mantle, and we have some of those in our data set. They are often reflected as pyroxenites. These pyroxenites are commonly formed when a melt or fluid fails to reach the surface and crystallizes out. And based on global compilations, we know that many cratons have small bits of pyroxenite within them. The length scales of these is not particularly well constrained, but we know they are definitely occurring there, most likely in the forms of narrow veins or dikes. So for all of these samples, we also have the pressures and temperatures at which they equilibrated at within the mantle using those thermobarometry methods described before. And so we can use the pressures and temperatures of these data to try and look at how density is varying within the mantle with the aim of trying to constrain how different metasomatic layers are contributing towards potential destabilization of cratonic roots. Now, there are a number of methods we can use to do this. Really, what we want to try and do is to constrain the temperature and the pressure and the density at those conditions. So to do that, we need three main things. We need equilibration, pressure, and temperature, which, as I mentioned before, we've got those constrained using the different thermobarometry method. We also need the end member proportions of the mineral. So we need, for each xenolith, we need to know how much olivine, clinopyroxene, garnet, etc. in that rock, but also the end member proportion of those different minerals. So how much forsterite and phalite are present, how much diopside, enstatite, hedenbergite, and so on are present. And provided that we have these different ingredients, we can use a number of different approaches or software to compute the density of those mantle xenoliths at that PT condition. There are two main methods that I use in this study. The first one is MageMin, which is a very similar method to thermocalc and perplex for those that have used those phase-equilibria softwares before. Another method is the approach of Abbas and Hacker, which is essentially a MATLAB toolbox or an Excel spreadsheet that uses this input data and computes out the density at the PT conditions. So we use both those methods in this data set. Essentially, they give the same density values when they're applied to the same samples. They use slightly different approaches, but when we apply them to the same xenolith samples, they give nearly the same values for density, which when you look at the sort of the underlying methods and equations of state that are used to calculate density, it's not a huge surprise. So both these methods are relatively robust in determining the density of which the xenoliths equilibrated at in the mantle. So when we apply these methods to our global data set of xenoliths, we can see on the plot on the left here, we've got the equilibration pressure, and we've got the range in density values. And we can see that across the data set, the values in density are scattering around values that we can't somewhat expect. We've got that characteristic or that diagnostic increase in density as we go higher and higher pressures. And across the different locations, again, we can see a relatively consistency in those values. The sort of the median range or the middle range in these density values is broadly consistent with what we expect from geophysical and geodynamic models of being a little bit above 3.3 grams per centimeter cubed. Now, perhaps one of the sort of the diagnostic or the interesting features on this plot here is that those gray symbols, which are those pyroxenites, those metasomatic rocks, across the depth range of our xenolith data set, those samples are almost always occurring at much higher densities. And this sort of comes back to what I was discussing before, in that these pyroxenites are causing sort of localized increase in the density of the mantle because they're concentrating many of these higher iron, higher aluminium and calcium minerals, and causing these sort of higher densities to be calculated. And this is just a histogram that's basically showing that range in density estimates. And again, that's sort of clustering around the range that we would expect for Cratonic lithospheric mantle. Now, in order to make some kind of sensible comment about the density structure and isopycnicity of the craton based on these density estimates, we need to be able to compare those density values with some reference value, particularly a reference value of the surrounding mantle. And to do this, we compare each density estimate of the mantle xenoliths at the same depth range with the convecting mantle. And to do this, we essentially calculate a density structure of the convecting mantle along the adiabat. So the temperature and pressure range, or temperature and depth range of the adiabat, gives us a relatively reasonable constraint as to what the thermal structure of the asthenosphere is across an equal depth range. And we can use those phase equilibrium models to calculate what the density of the convecting mantle would be along this depth and temperature range. Now, the input composition we use for those calculations is KLB1, which I think most people would agree, or hopefully agree, that KLB1 is probably the best natural analog we have of the composition of the fertile undifferentiated mantle. So essentially what we're doing is that across this entire depth range of the mantle adiabat at a potential temperature of 1315, we are calculating the density of KLB1. Now, the purpose of this is that for each of these individual xenoliths we have, we want to compare its density within the lithosphere with the theoretical density of the asthenosphere at the same depth range. Remembering that I said that cratons that are perfectly isopycnic will have a density structure that essentially matches the asthenosphere across an equal depth range. So if the cratonic lithosphere is perfectly isopycnic, then we would expect the vast majority of these xenolith samples to have density values that closely match that of the convecting mantle along that adiabat. So this plot just basically, this is where we, it's a very simple diagram showing how we're calculating these. These are all done in MageMin. For those that are interested, you can read the methods described in Real et al. But essentially, this is a phase equilibrium modeling program where we're computing the density of the KLB1 along that adiabatic value. So this plot here shows on the x-axis the density estimates of the mantle xenoliths. So they're essentially density estimates of the lithosphere. And the y-axis is the density estimates of the asthenosphere or the convecting mantle at the equivalent depth of those xenoliths. And so as I discussed on the previous slide, cratons or cratonic mantle rocks that are perfectly isopycnic will have a density value that matches the asthenosphere at the same depth range. So all these are computed at the same depth. And we can see that the vast majority of those colored peridotite xenoliths are cluttering or clustering along that sort of one-to-one line with a little bit of noise. Obviously, we are carrying a large number of uncertainties from our thermobarometers, our mineral mapping to calculate the end member proportions, and also the phase equilibrium modeling software. So I think it's unreasonable to expect they're going to plot exactly on that one-to-one line, but there is a little bit of noise there. But we can see across most of the data set, those ranges in lithosphere density are broadly matching those of the asthenosphere at an equal depth, which, as I've stressed a couple of times now, is diagnostic of a perfectly or near perfectly isopycnic mantle. Now, obviously, the exception here is those grey samples. Those are the pyroxenite samples, and we can see that regions where those pyroxenites, those metasomatic veins and metasomatic dikes are occurring, they've almost always got a much higher density than what is the density of the surrounding mantle at the equivalent depth. So these are essentially representing bits of really dense mantle that are incorporated within cratons that are denser than the surrounding asthenosphere. And by definition, these are rheologically and dynamically unstable within the cratons, which is a quite important constraint to put on these rocks. So this plot here is just basically showing that previous plot of where we've got the density of the lithosphere compared to the density of the asthenosphere calculated in equal depth range. And we can see that the vast majority of those samples are sort of clustering within that range of isopycnicity. Again, there's a little bit of noise, but this is well within the regions that we sort of expect for these methods. The important thing is that we don't see these peridotite rocks clustering to much higher or lower values. They're broadly around the values of isopycnic or neutrally buoyant density values. Now, as I said before, we've got these pyroxenites that are significantly more dense within the mantle. And these are the materials, these are the rocks that are of interest for actually causing destabilization or removal of the Cratonic lithospheric mantle. At least based on these values that we've got for the peridotite xenoliths, if we have cratons that are perfectly comprised of these peridotite mantles, it would be extremely, extremely difficult to cause any form of destabilization, removal by density-driven processes if these are the rocks that are occurring. Now, obviously, with the exception, if we've got rocks that are dominantly pyroxenites within the mantle, and these are occurring over large length scales, then it might be possible to cause destabilization or removal of cratonic roots if these rocks are accumulating on large enough length scales. Now, the length scales over which these pyroxenites need to occur is an important question to ask. Essentially, how much pyroxenite or how much of these dense lithologies do we need in the mantle in order to actually cause some kind of net removal by density-driven processes? And in order to answer this question, we've conducted a very simple dynamic model that essentially explores that. So this plot here is essentially showing on the y-axis the radius of a pyroxenite body in the mantle. We are modeling this pyroxenite body in the mantle as a sphere. Now, this is obviously a gross simplification, but this is sort of the best case scenario. If we were to model the pyroxenite as a more complex geometry like a prism or some kind of rectangle, this would just result in slower sinking rates. So our model is optimized for the best possible scenarios to removing these dense pyroxenites from the mantle. The x-axis is the viscosity of the surrounding mantle of which this pyroxenite body is occurring in. And for each of these models here, we've got different density contrast between that pyroxenite body and that surrounding mantle that it's occurring in. So the two density contrasts that we make here are 100 kilograms per meter cubed and 300. And these are broadly consistent with those models, those density estimates that we have from our xenolith data set. So when we look at the variation in density between the peridotite and the pyroxenites, the upper range is sort of towards 100 to 200 kilometers different, 200 kilograms different. So these models are set up to try and match those observations. Now on these plots, we've got the coloring, which essentially represents the velocity at which that pyroxenite body is sinking through that peridotite mantle. Now for reference on these two plots, we've got this bold line here. And this bold line essentially represents the conditions at which that pyroxenite body would sink approximately 90 kilometers in 3 billion years. And so we mark this bold line on simply as the absolute upper conditions as to what is geologically realistic. I think it's unrealistic to expect sort of sinking timescales beyond this year. Now, sinking 90 kilometers in 3 billion years, if we wanted to try and remove that pyroxenite body faster, perhaps on the length scales of the Wilson cycle or the length scales of origins, really our only option is to change the viscosity of the mantle, which perhaps for cratons is not particularly a reasonable change to make because the viscosity of the mantle is relatively well constrained, at least for the convecting mantle is probably around about 10 to the 21. Decreasing that even further is quite unrealistic. The other option is to increase the size of the actual pyroxenite body. So in this particular scenario here, where the pyroxenite body is sinking through the mantle on those timescales, the size of that body is around about an upper range is about 20 kilometers in size. So a pyroxenite body that is 20 kilometers in size will sink through 90 kilometers of lithosphere within approximately 3 billion years. If we want to remove that pyroxenite body faster, then we have to increase it even larger. And at least within our observations of the Cratonic lithospheric mantle, there is not a huge amount of constraints or observations that pyroxenite bodies are occurring any larger than that. So these are the two models there. This condition here is slightly lower range because of the density contrast, but generally these two models suggest that pyroxenite bodies that are on the length scales of perhaps 10 to 20 kilometers require quite significant timescales to be removed. Now, for those that have worked on mantle xenoliths and particularly metasomatic xenoliths within the mantle, such as these pyroxenites, I think many would agree that these are typically occurring on much, much smaller length scales, often on the scales of maybe centimeters, millimeters, or quite rarely meters in scale, and definitely not on the scales of sort of 20 kilometers. So at least in terms of these pyroxenite bodies, we don't think there's particularly strong evidence that that they are contributing towards destabilization simply because the conditions for them to be removed are quite extreme. Now, the case can be made for eclogites. I'm not going to discuss too much about eclogites here, but that's obviously a completely separate story as to how they can contribute towards destabilization. But at least here in terms of the metasomatic introduction of pyroxenites in the mantle, we don't think that they are contributing towards destabilization because they are simply not occurring on large enough scales to be removed. So obviously the implications of that is that these pyroxenite bodies are probably causing or contributing towards sort of localized changes in the density or increase in the density, and possibly locally decreasing the solar's temperature, but they are definitely not contributing towards massive 50-kilometer removal of the Cratonic lithospheric mantle, at least based on these models we've proposed here. So that's broadly where I'm going to finish off. I discussed at the start that many of this data that I've used here is partly from work that I've done in Australia, but the vast majority of these samples are from work that many of the people in the audience have done and many people in the sort of mantle petrology community have contributed towards too. These data sets are all available. The most updated version is on Zenodo, so feel free to download that. The topics that I've discussed here are in part discussed in a few recent papers, and I'd be more than happy to discuss those in detail with people that are interested. But crucially, for those that are after the data set for their own research purposes or for exploration, that is all publicly available. But I do stress that many of this is from the hard work of many people that are sort of working mantle exploration or diamond exploration and mantle petrology research. So only a very small proportion of it is my own samples. Now, with that said, I'll quickly thank the main people that have sort of been involved with this, stressing that many of these ideas and these topics are my own, and the co-authors may not necessarily agree with everything I say, but a few of them are co-authors. So I will thank Alex Copley, Keith Priestley in particular, Dan McKenzie, James Jackson, and Simon Lamb, and importantly, Maya Kopilova for the invitation, and Gary for the help as well, and everyone for listening. So Thank you very much. I'm more than happy to answer any questions for those that are interested.
Thank you, Zach. That was a great presentation, and it is a very robust comparison of the LAB depth through time and the density estimation of the cratonic lithosphere and the asthenosphere, and it is dealing with a large data set that you have. So now we have 10 to 15 minutes of the Q&A section, so feel free to turn on the microphone and video to ask your question, or you can also ask your question in the chat box. So the floor is open.
I'll give it a go. It's Herman Grutter speaking.
Oh, wonderful.
Hi,
Hello,
Zach.
Herman.
Nice to hear your story from my own alma mater. I actually, I remember Dan McKenzie coming up to my studio at Cambridge and talking xenoliths with me. So that's an interesting co-author that you have.
Yes. Yes.
I have a question, but I'd like to share my screen.
Yep.
And then I also, for everybody that's involved, I'd just like to make an announcement regarding a paper that's been withdrawn. I can't remember how to share a screen. Oh, here we go. There we go. So I'm sharing, I just took a clip from one of your images, Zach.
Yep. I can't see your screen, I don't think. Oh, yep. There, yep, now I can see it. Yep.
Okay. And I'm interested in the little inscription on the top right-hand corner there, which says,
Yep.
The rate of change of temperature with time
Yep.
assumed for that diagram is nothing.
Yep.
Does that mean that you're saying that the isentrope that you've assumed as your reference isentrope
Yep.
is being invariant for the purposes of that diagram?
So yes, absolutely. I mean, the models are made using a potential temperature of 1315, and the basis for that, I think, is that we don't agree that the potential temperature was significantly higher in the past. So we conduct some models, and there are some models in the appendices where we test models using a rate of change of 50 kilometers, but that would be the absolute upper range as to what we would accept. Now, I completely understand that there would be many people that would probably disagree with that in terms of thinking that potential temperature was that high.
If you assume that isentrope temperature change isn't as extreme as some people have made it, you know, 200 or 250 degrees centigrade since the Archean. How do you justify the extent of depletion that we see in cratonic roots then?
Well, I think it depends.
Do that if the isentrope or the asthenospheric melting, it doesn't matter at which pressure, was at 200 degrees centigrade hotter than it is today.
Well, I think you could easily explain many of those observations with hotter plumes.
Sorry,
so
what?
Not necessarily hotter asthenospheric mantle, but hotter mantle plumes. So you could, I think you could argue that you could cause the same depletion in the cratonic lithospheric mantle without having to have significantly higher potential temperature of the convecting mantle, but just by having slightly hotter mantle plumes. And you would be able to explain the occurrence of komatiites as well, and I think other observations. But I'd be curious as to what your thoughts are on that. But I mean, I've spoken with a number of people that I think are happy with a rate of change of on the order of 50 kilometers at an upper range. But there are many authors that would also argue that the potential temperature was on the order of 250 kilometers.
Okay,
So
that's a neat answer. Thank you. I wanted to share something else quickly, so maybe I have to reshare my screen. And it's this. I noticed that you quoted in 2 slides a paper by Sebastian Tapper that appeared in EPSL in 2018.
Yes. Well, I mean, I mentioned them at the start of the talk in terms
No.
of
Okay.
the locations and occurrences of kimberlites.
Zach, you might not know this, but that paper's been drawn.
Uh, yes, I mean, the images I was using was simply just to show the locations and
Look,
age distribution of kimberlites.
all I'm saying is if you're an academic
Yep.
and you apply these academic rules,
Yep.
please don't ever quote that paper again. It doesn't exist.
Okay.
The reason for it, the removal is on the bottom right-hand side of this image. The article was removed at the request of the EPSL editor due to unauthorized use of data.
Okay. Yeah, I mean, yeah, I guess, I mean, sure you can understand me here, Herman, that the plots I was showing there were simply just to show the age distribution and occurrences of kimberlites, and there's not.
I
Any-
understand why you used it. It's a convenient reference to use for that purpose.
Yep.
I'm just pointing out that it's illegitimate data.
Okay. Well, um, I can see that that was withdrawn. It must be very recently then, so I do apologize if that's uh, sort of I've missed that. But yeah, thanks for pointing that out, Herman.
Okay. Yeah, and it's valid for everybody else that's in the academic sphere um, and who deals with this type of stuff, kimberlites and dynamics of the cooling Earth. So yeah, just remember, don't quote that paper. Thank you. That's all for me from my side. Thanks, Zach.
Thank you, Herman.
Zach, can I follow up on actually on the same slide that you discussed with Herman?
Yep.
So can we go back to that slide? So it shows
Uh,
the paleo lab against the geophysical lab.
that one?
Yeah, this one.
Yep.
Yeah. Two questions on that.
Yep.
So the first is when I'm looking at the data, what jumps at me is that you have examples of thinning. So not China craton, but also some other examples from South Africa and also from Siberia. But you never have examples of thickening of the
Yep.
cratonic mantle. So, and it might be an interesting pattern. So what do you make of it? That we only see thinning, but yeah, not thickening. So that's the first part of my question.
Yeah, no, it's a completely reasonable question. It's a very interesting one. I mean, I think there's a number of these locations where you've got intracratonic rifting that's occurred, and there's possibly some remnants of that that is being recorded in the data set. But yeah, the absence of thickening, I think, yeah, I really can't explain that. I think there's some capacity. It may depend on which tomography model we may use. I think if we may use a slightly different model, they might shift slightly, but there's definitely not really any of the evidence that there's been significant thickening of any of these cratons. So I think, yeah, there's verdict out on that, and I'd be curious to hear what any other people's interpretations are. But I think overall, sort of on the length scales of or the time scales of this data set, we're not seeing really any sort of secular changes, which I think was the thing that we were most interested in. There's not sort of this net thinning or net thickening of lithosphere through time, but maybe some smaller localized variations.
Mhm. Yeah, yeah, thank you. And my second part of question is on Melita kimberlite. So can you tell us more about that kimberlite? How
Yep.
well preserved it is? Do we have that metamorphosed or unaltered? Do we have a lot of material from there?
Yep. Yeah. So that's it is an occurrence in the Yilgarn Craton in Western Australia. It's so a lot of those samples I got as a result of concentrate that's was provided from the West Australian Museum. Uh, Vast majority of that is just garnet and clinopyroxene. So I haven't done much of the garnet compositions, but the temperatures and pressures that we get from the clinopyroxene thermometry give us a sort of a lithospheric thickness on the order of a bit over 220 kilometers. But in terms of the whole rock, actually, the actual kimberlite pipe, I'm not there might have been a couple of studies, perhaps by some of the people at University of Western Australia, I think did some work maybe on that. Definitely on terms of some of the other occurrences in the Yilgarn Craton, but um, yes, it would be very nice to try and get some samples, some more samples from there. There'll definitely be drill core and material available for people that would be interested in actually working on the pipe composition at the probably the Geological Survey of Western Australia. But in terms of actual xenolith material, most of it will just be single grain clinite pyroxenes and garnets and probably a lot of chromites as well. But if people that are interested in trying to get some core for that, I can easily point you in the right directions. But it's all from the West Australian Craton, the Yilgarn Craton.
Hi, Zach. Can I ask you a question?
Absolutely.
Yeah, yeah. Oh, no, excellent presentation. I really enjoyed it. I was just curious to know what seismic tomography model do you use? Because, as you know, there's global surface area models like, SL 2013 and so on. And then there's obviously ones that are regional, by continent or by
Yeah.
craton. So
Yeah.
obviously that would have an impact on when you do these difference calculations.
Yeah, absolutely. Yeah, it's a fantastic question. So for this particular model, we use CAM 2023, which is Keith Priestley's particular model. Um, so I completely agree with you. If we were to, probably a really interesting thing would be to start using regional models. So for Australia, there are a number of suitable models like Fishwick and Rawlinson that would provide very intricate variations in the lithospheric thickness. And indeed, there's work that I'm involved with Mark Hoggard that sort of looks at that on smaller scales. But um, yeah, I think in terms of the global model, we're using the Cambridge models, but there's opportunity to also compare it with Sergei Lebedev's model as well. But yeah, I think that's probably the next step is to sort of look more on regional scale models.
Yeah. Okay, thank you.
Hi, Zach.
Oh, hey, Gary.
Hi, how's it going? Great talk. Really interesting. I was very interested by the plot you showed of the CPX just versus pressure and temperature, including the diamond data.
Yep.
Where you said, yeah, you can go to
Should be there. Yep.
this one.
Yep.
Yes. Where it looks like the range of pressures and temperatures is very similar to that of the xenocryst. And you said, on a global scale, this holds. Does it hold on, say, a more regional scale or per craton or per location? Does the pressure and temperature of these diamonds match with particular areas?
Well, that's probably a question you'd probably be able to answer a little bit better than me. But yeah, I think perhaps I think most of them it would generally agree, at least from my observations. Perhaps within the Cupval Craton, there might be some samples that might give a slightly different gradient, and that's I think the basis of a lot of the work that Emma had done, perhaps. But I think, at least on my observations, I think it's generally sort of plotting within the same PT trajectory for the vast majority of it. But I'd be more than happy to be proven wrong if someone were to sort of redo that and have a look at the pressures and temperatures of some of those individually. But at least from my observations, I think the vast majority of them are recording that similar range in PT values within individual cratons.
Yeah, cool. Yeah, no, I agree. So yeah, I think you're right. Yeah, that's great. Thanks.
Is there more question from the audience? Okay, if not, thank you for all the questions and all the comments. This will be the end for today's section. Thank you, Zach, again for his presentation, and thank you everyone for attending. And you're welcome to stay behind for a chat, and we encourage you to turn on the video to chat. if you're convenient. Okay, so I'll stop the recording now.